Hi, everybody. It's Mr. Roy. We've talked in this course about one of the huge ideas in physics, which is conservation of energy. And today we're going to talk about another huge idea in physics, which is related to momentum. It is conservation of momentum. We're going to start by looking at conservation of momentum just linearly, so in a straight line in one dimension, essentially. So we've got up, down, left, right, north, south, east, west. We're just looking at one dimensional to start with to keep it simple, and we're going to look at conservation of momentum. Here we go. A lot of students really like doing conservation of momentum because it feels really familiar. It's going to use a lot of the skills that we've built up throughout the course of the semester, and we're going to get to apply them to something that's a little bit different, but in ways that feel very familiar. So here's our law of conservation of momentum. It says that when two or more objects collide, we're going to stick with two for now, the collision does not change the total momentum of the two objects. Emphasis on total. The sum of the momentum of the system. Whatever momentum is lost by one object in a collision is gained by the other. The total momentum in the system is conserved. Now, Isaac Newton actually thought about his third law of motion when he first conceived of it in terms of the conservation of momentum. So this is really the foundation for Newton's three laws. Let's consider two objects that are interacting with one another. We've got the blue one, which I called number one, and the purple one, which I called number two. In our little diagram here, we have them coming towards one another, hitting one another, and then reflecting. And these blue arrows actually represent, oh, no, I want you to write. There we go. These blue arrows actually represent the momentum. That's the momentum of object one, and we would say that's the initial momentum of object one. Here we have a momentum vector. That's our momentum of object two, and it's the initial momentum of object two. Now you could put the two and the I in either order. It doesn't matter to me. You'll see different things in different books, and I might kind of like switch up which I'm doing. After the collision, we've got object one, and this is its final momentum. And then after the collision, we've got the momentum of object two, final. And when we add these vectors together, we will end up with the same momentum, noting that we do have bigger magnitude total as it appears in the first one, but they are in opposite directions, so they're going to cancel each other out to a degree. So when you add these two arrows together, the initial and the final, you're going to find that the sum of them is the same. Now we could write this mathematically, right? We can say the momentum total initially, put a vector hat on it, equals the total momentum final. The momentum before the collision equals the momentum after. Now, since there's two objects, I could go a little further with this. I could say the momentum of my first object, initial, plus the momentum of my second object, initial, equals the momentum of my first object, final, plus the momentum of my second object, final. So I've just written that same conservation of momentum equation with all of the parts involved. I could break this down even further, right? Momentum for object one is actually the mass of object one times the velocity of object one. Now that is the initial velocity, of course, and the mass of object two times the velocity of object two, initial. That's going to equal the mass of object one times the velocity of object one, final, and the mass of object two times the velocity of object two, final. Now you could add more objects, right? We could do this with 3 objects, we could do this with 5 objects, doesn't matter. The total momentum of the system is conserved even when there are these interactions, these collisions, except if there's outside forces acting on things. So if there's no outside forces, momentum is conserved. Now you can see how this would come into play in things like asteroids colliding with one another and us trying to find their trajectory. And it happens with planetary bodies, but also this could happen with pool balls on a billiards table. Same kind of idea. This also happens with car crashes and when they're like doing tests with crash test dummies. it's this same kind of concept. Anytime we have two objects colliding with one another, this will happen. And a really important application of this is particle physics, when particles are colliding with one another. And so it's one of those physics concepts that can deal with the very small and the very large, and is an interesting principle of conservation. Pretty neat stuff. Okay, let's move on to our next page here. We could look at some different ways we could have this. We could have, like we saw in our first one, two objects that are separate. They collide and then they go apart separately. That's very normal. If they collide and bounce off perfectly, we would call that an elastic collision, a perfectly elastic collision. But we could have some other situations too. We could have a situation called a perfectly inelastic collision. And I like to think about elastic is bouncy and inelastic would be like sticky. So if two objects stick together after they collide, like two football players, one tackles the other and they stay together, we add their masses together and they move on with a common velocity. So how would we write that mathematically? We'd say, well, we got our momentum of our first object, right? So we'd say that momentum we could write as mass 1 times velocity 1 initial plus the mass 2 times velocity 2 initial. So that's our two football players. That's their momentum. We could say they run into one another and they stick together. Now we're going to put their masses together like this in a bracket. And then we'll say our final velocity. We don't need to say if it's the velocity of object 1 or object 2, in this case, football player 1 or football player 2, because they're moving together. So their velocity is the same. So this is a way to simplify our equation a little bit when we know we've got a situation where two objects stick together. We could also find ourselves in a situation where objects are together and then they separate. This happens anytime there's an explosion. So a common example of that would be like a hunting rifle or a BB gun or a cannon. Yeah, now I am trained to fire cannons. I worked at a historic site for a number of years, Fort William Historical Park, so I like to use cannons as an example. They're stationary, the cannon and the cannonball, and then there's an explosion, and the cannonball goes to the right, and the cannon is going to recoil and go back to the left, and cannons are actually designed to handle this. Ropes prevent cannons from rolling too far back on ships or docks so that they don't injure someone necessarily. But you do want that cannon to move back so it can deal with that momentum that it gets. So we could say if two objects are together and then they separate, like a cannon and a cannonball, we would call that an explosion. We would have a situation where initially we've got the mass of one object, like the cannonball, and the mass of the second object, like the cannon. They're together, and this would be their initial velocity. That's the momentum of the system. Now, in many cases, this whole side is going to be 0 because the initial velocity would be 0. That's the case in anytime we're dealing with like a firearm or something like that, or an explosion. Often the initial velocity will just be 0. And then after the explosion, we say we've got our cannonball, and we've got our cannon, and they're moving off in separate directions. So we have to have them separate. Now, instead of, in this case, if you're dealing with a cannon and a cannonball, instead of using M1 and M2, I might label them MB for ball and MC for cannon. And that's a perfectly good way to do it, to help kind of keep your math a little better organized. Okay, so you may have situations where the masses start together and then separate, or the masses start separate and then come together, and starting with your formula like this can actually save you a little bit of time. Let's try a couple of these examples out and see how we do. A 1 kilogram ball moving with a velocity of 2 meters per second to the right collides head-on with a stationary 2 kilogram ball. After the collision, the 2 kilogram ball has a velocity of 1.2 meters per second to the right. Calculate the velocity of the 1 kilogram ball following the collision. First of all, we got to pick our directions. So let's do that. I'm going to pick left and right. So here's right and here's left. And I think I'm going to choose right as my positive and left as my negative, although that is an arbitrary choice. Okay, so we'll say, all right, we know that our total momentum initial equals our total momentum final. The momentum before the collision equals the momentum after. We're going to label our objects object 1 and object 2. I'm going to call the 1 kilogram ball object 1 and the 2 kilogram ball object 2 to kind of keep it nice and organized. So the mass of object 1 times the velocity of object 1 initially plus the mass of object 2 times the velocity of object 2 initially is going to equal the mass of object 1 times the velocity of object 1 final. Oh, sorry, that should be a 1, not an I. Plus the mass of object 2 times the velocity of object 2 final. Okay, now I got to sub some stuff in. There are going to be some zeros in here, right? Object 2 I know is initially stationary. So it's going to have a velocity of 0. So that means this whole term is going to become 0. So rather than sub it in, I'm just going to cross it out and know that it becomes 0. The mass of ball 1 is 1. The velocity of ball 1 is 2. And it's to the east, so I'm going to write it as a positive. The mass of ball 1, again, is 1. The final velocity of ball 1, we don't know. That's what we want to find. The mass of ball 2 is 2 kilograms. And the final velocity of ball 2 is 1.2 meters per second to the right. So again, I'll put it as a positive number because it's to the right. Let's simplify this a little bit. 1 times 2 is 2. We've got V1F. 2 times 1.2 is going to be 2.4. And then we subtract 2.4 from both sides. We're going to end up with the final velocity of our ball number 1 is negative 0.4. Now, a negative tells me we're going to the left. So let's write our final statement here. 0.40 to have 2 significant digits, meters per second. Now, I could write left. I could also just draw an arrow like that to show direction. That would be a fine way to do it, which is what I'm going to do in this case because it makes it look nice. Okay, there we go. We figured out the final velocity of ball number 1, accounting for the fact that momentum is conserved. Let's try another guy here. A hunter fires a stationary 5 kilogram rifle. Calculate the recoil velocity of the rifle if it fires a 50-gram bullet with a velocity of 300 meters per second. Assume the rifle is initially at rest. I guess that's a little redundant because it does say a stationary rifle and then says it's at rest. So maybe that was obvious. Okay, we got to choose our directions. Now, we don't have any directions listed here, north, south, east, west, or anything like that. So I'm just going to choose forward and back as my directions. Forward will be the direction that the bullet is shooting. Back is the direction that the gun will recoil. We know this is true, right? If we've ever seen like movies and TV, or if you ever shot a firearm yourself, if you're into hunting, as lots of people are here in Thunder Bay, when you shoot a firearm like that, the bullet goes forward and the gun will recoil backwards into your shoulder. Okay, so let's deal with our conservation of momentum. We're going to say our total momentum initial equals our total momentum final. Those are going to be equal to one another. We say that in the beginning, we know they're together. So we've got the mass of the bullet plus the mass of the gun times the initial velocity. Now they're together, so I only have to write the initial velocity. That's going to equal the momentum after, which is the mass of the bullet times the velocity of the bullet final plus the mass of the gun plus the velocity of the gun final. Now, are any of these 0 that we can just cross out? Yes, the initial velocity of the bullet and the gun is 0. So I know there's going to be a 0 in there. So this whole term is going to end up being 0. So I'm going to end up with 0 equals the mass of the bullet is 0.05 kilograms. That's 50 grams. And we know it's moving at 300 meters per second forward. So I'll write it as a positive. The mass of the gun, that's 5 kilograms. The velocity of the gun final, we don't know. We're going to find out. But we know we should get a negative answer. It should be backwards. Okay. 0.05 times 300, that's going to end up being 15. Do a little algebra here. Let's move the 15 over to the other side, and then let's divide both sides by 5. We're going to end up with velocity of our gun final is going to be -3. So that would be in meters per second, and that would be backwards. Let's write that as a final statement here. The velocity of our gun final is going to be 3 meters per second, and I'm going to one significant digit because that's what is included in the input data, and it's going to be backwards. So I'll write backwards to make it clear. And we'll put a box around it to show that's our final answer. Okay, let's have a look at some things that are going to stick together. A 6.0 times 10 to the 3 kilogram rail car moving at 2 meters per second east collides and couples. That just means they join together, right? Train cars have these joiners that when they run into one another, they join together and clamp together. It couples with a 3,000 kilogram car moving west at 3 meters per second. Now it's a railway car, like a train car. What's the velocity of the pair after the collision? So this is a situation like the football players where they're separate and then they come together. Collisions where objects couple together have a special name. We call them completely or perfectly inelastic collisions. Think about two balls of Play-Doh running into one another and sticking together. They don't bounce off, so they're not elasticy. They stick together. So we call these collisions perfectly inelastic collisions, or sometimes you'll see them called completely inelastic collisions. Okay, so for this one, we're going to say we got to choose some directions. East and west looks like what we're going to have here. So I'm actually going to put it up here so I got a little more room. Here's my east and here's my west. Let's call east positive and west negative. Okay, so we know our momentum total initial equals our momentum total final. Okay, so we know that these things are starting separate. So we're going to say, I'm going to call the 6,000 kilogram, I'm going to call that car number 1, and I'm going to call the 3,001 car number, rail car number 2, in order to keep this straight. So we'll say the mass of train car 1 times the velocity of train car 1 initial, plus the mass of train car 2 times the velocity of train car 2 initial. That's going to be equal to, now they couple together, so we can say the mass of 1 plus the mass of 2, and their final velocity we know is going to be the same because they're stuck together. You can actually see this at rail yards. It happens all the time. Okay, let's plug in our numbers here. For a mass of our first one, we've got 6,000 kilograms. We know our velocity is 2 meters per second to the east. Our second one we know is 3,000 kilograms. And we know our velocity is to the west. So I'm going to say -3 meters per second because it's traveling west, which we defined as negative. Mass 1 plus mass 2, 6,000 plus 3,000. That's going to make a total of 9,000. And we don't know what the final velocity is. We're going to find that. Okay, let's do a little bit of work here. We're going to end up with 12,000 minus 9,000 equals 9,000 times the final velocity. 12,000 minus 9,000, we're going to end up with 3,000. Divide that by 9,000, we're going to end up with a final velocity of a third, and we could write that as 0.33333. Okay, now let's round that off for significant digits. Looks like we've got 2 significant digits. This is our lowest amount of sig figs in our data. So we'll round this off to 2, and I'll say 0.33 meters per second. Now it was a positive answer, and we know the positive numbers mean east. So that's our perfectly inelastic collision when two things stick together. Last one, here we go. An 80 kilogram hiker wearing a 20 kilogram backpack is standing on a stationary 25 kilogram raft. If he throws his backpack off the raft with a velocity of 8 meters per second, west, determine the resulting velocity of the raft and hiker. Let's pick some directions. I'm going to choose east as positive again, I think. Now we'll say, let's do a little picture here. Here's our log raft, and here's our hiker standing on it. And they're throwing their backpack. There's a strap there and a strap there. They're throwing it that way. That means the backpack's going to move that way, and the hiker, to conserve momentum, is going to move back the other direction. But the hiker probably weighs a lot more than their backpack. In fact, we know they weigh 4 times as much. So the velocity is not going to be equal. The backpack's going to move a lot more quickly than the hiker. Let's jump in with our formula here. We know our total momentum initial equals total momentum final. I am being a little picky about writing this out every time, but this is just to remind me so that I'm being really good and I'm not going to make any mistakes. I'm being really clear about what I'm doing. We know first they're together. I'm going to use B for backpack and H for hiker and raft combo. Okay. When she did get some time last year, just never hardly ever. I think I started playing She finally became a pit bull for 3 years. Yes. Okay, looks like they're done in there. I'm going to head back in and finish my recording. See you tomorrow. Yeah, have a good one. You can go ahead and close her up when you're going. Thanks, Abby. See you tomorrow. Okay, let's jump back in. Sorry, I had to pause the recording there for a minute. We said our total momentum before is going to equal our total momentum after this exchange where our backpacker or our hiker throws the backpack. They're together to start, which means I can write mass of the backpack plus mass of the hiker and raft together, and their initial velocity, because they're traveling together as one to start. And then they're separated. So we got our mass of our backpack and our velocity of our backpack final plus the mass of our hiker and the velocity of our hiker final. Put some vector hats on there. Now, initial velocity I know is going to be 0, right? They're just sitting there standing on the raft, not moving around. So that means if that initial velocity is 0, I can get rid of that entire term. I'm going to end up with a 0 on this side. Let's sub in for the mass of the backpack, which we know is 20. The velocity of the backpack final, we know it's moving at 8 meters per second west. West is negative, so I'll put a -8 on there. Then I've got the mass of my hiker. which I have to add to the mass of the raft. So hiker is 80, raft is 25. That's 105 total. And my velocity of my hiker, velocity of my hiker final is what I want to try and figure out. Okay, so I'm going to do some multiply 20 times -8. Then I'm going to move that over to the other side, and then I'm going to divide both sides by 105. And I'm going to find that my final velocity of my hiker on the raft is going to be 1.52381. Let's round that off for significant digits. We're going to go to 2 significant digits. So that means my velocity of my hiker final is going to be 1.5 meters per second to the east. Finally, let's just look at a conceptual question here. A child throws a snowball at a tree. The snowball sticks to the tree and stops. Does this violate the law of conservation of momentum, that both the snowball and the tree are stopped before there was momentum from the snowball at least, and after there's no momentum in either of them? Does this violate the law of conservation of momentum? Well, here's the big idea here. This would not violate the law of conservation of momentum because the tree is actually attached to the earth, which combined has a huge mass. So the change in velocity of the tree-earth system is so small that you can't perceive it. It's kind of like how with Newton's third law, the earth pulls on us, we pull back on the earth. We don't actually notice the earth moving because the mass of the earth is so gigantic that that small force doesn't really affect it at all. Similar with momentum. The change in momentum of the tree and earth system is so tiny that you're not actually able to perceive it, even though that tree might move the tiniest bit. Okay, that's it. I hope this lesson has helped you understand the law of conservation of momentum. Now time for some practice.